Hey everybody, welcome back to the next installment of this. Today what I wanted to do is talk a little bit about just some properties of water. And last time we were talking a little bit about hydrogen bonding right at the end, and that hydrogen bonding is going to have a whole heck of a lot to do with how water interacts with other things. So this is sort of what I was showing you before. It's not sort of what I was showing you before, it's exactly what I was showing you before. What we have are some, let's see, some negatively charged sides of oxygen and some positively charged sides of hydrogen. And here's another negative charge, here's some positive charge, here's a positive charge, so on and so forth. And what we actually see here is that, let's change colors, the positive side of a hydrogen is attracted to the negative side of the oxygens. They stick together. They stick together much like magnets do. Um, you guys have all played with magnets, I'm sure. I still love to because I'm at heart childish and think that magnets are cool. But you have a positive side of a magnet and a negative side of a magnet, and those things stick together because of their opposite charges. Water does the same thing. Now, here's the thing. It's not a super strong bond. It's not nearly as strong as the covalent bonds that are holding the oxygens to the hydrogens, or even as strong as a ionic bond holding something like sodium to chlorine. So these hydrogen bonds can be easily broken, and the easiest way to break hydrogen bonds is to add energy to them. We'll get to that in just a second. Here are some examples of how hydrogen bonds give very specific properties of water. One of those is cohesion. So water molecules tend to stick together. That's what we were just talking about on that last slide right there. You have one water molecule sticking to another water molecule. Water itself, every molecule there behaves like a little magnet, and it allows for the water to not fall apart. If you can imagine, sort of melting sugar, or if you leave like sugar or something like that in a bag, it absorbs a little bit of water and it sort of turns into a brick. That's kind of like what cohesion is. If it's not cohesive, if the sugar's not cohesive to itself, then it kind of falls apart. It's granular sugar. Now, this can actually give us some pretty cool properties because it allows water to stick to itself and be drawn up inside of plants. It helps us transport water and nutrients throughout plants, many times against gravity. It's also responsible for stuff like surface tension, which you've probably seen things like bugs or something being able to walk on water. And that's all because of cohesion. Another property of water is called adhesion, and that's water's ability to grip other things, like the side of a straw, or in this case, the xylem of a leaf, which are sort of like little straws inside of leaves or leaves. So, because of water's polarity, not only will it stick to itself, it'll actually stick to the cells surrounding the tubes of this xylem. It's why you can actually drink through a straw. Now, capillary action is water's ability to be drawn towards a negative pressure. So in this case, what we're talking about is you create a negative pressure in the leaf of a tree or something. And so how you do that is you open up pores and you let water evaporate. Well, as water evaporates, it's drawn up through the roots and it's brought up to the leaves themselves. Okay, so it's almost like a giant straw. In fact, just like in a straw, you create negative pressure when you're drinking a Coke or a milkshake. And the way that this happens is you suck on the straw, that creates a negative pressure and it draws all that water up. And it's able to stick together because of capillary action. This will happen with very, very little external pressure pushing down on surrounding water, or very little negative pressure drawing it up. So it works really efficiently. Water also has the ability to control temperatures in a couple different ways. The first is it has a very, very high specific heat. And what we mean by that is it has the ability to absorb heat from the environment. Now, how does it do that? Well, remember those hydrogen bonds that we keep talking about? So those actually have the ability to absorb energy. If you put more energy into water, what happens is these water molecules here sort of start wiggling around. Um, and the reason that they wiggle around more is because as you add this energy into these hydrogen bonds, they get a little bit farther apart from each other. They're able to absorb this extra energy, and the water molecules themselves kind of absorb that sort of like a spring. So water has this really high specific heat, meaning the air temperature can change drastically, but the water itself holds on to the heat that it's sort of stored. Um, that helps stabilize ocean temperatures. That's really beneficial to things that live in the ocean. I think probably the easiest way to see something like this is if you're at the beach uh, in, say, the wintertime. The water near the beach in the wintertime, or the air temperature around the beach, is always more stable than farther inland. So if you go to Pensacola Beach and it's wintertime or something, the air temperature is 50 degrees, um, it's probably going to be a little bit warmer at the beach than it will in, say, Cantonment or in Milton, or even, yeah, we'll just stick with those two for right now. So what's happening there is the ocean itself is has absorbed heat, and it's able to stabilize the air temperatures around. Where if you go inland towards Cantonment or Milton or something like that, there's not nearly as much energy, and so the temperatures fluctuate a lot more. Another way of thinking about this is the temperature differences between night and day in some place like a desert compared to a rainforest. A rainforest, the differences between day and nighttime temperature are negligible because there's so much water in the air and the ground and everything else that the temperature really doesn't fluctuate a whole lot. Now, I'm also sure that you know that in a desert, it's just the opposite. Once the sun goes down, even though it may have been really hot during the day, it's really cold at night because there's no water there to hold on to that temperature. Here's another one, evaporative cooling. So water has the ability in very small amounts to cool off or to dissipate heat energy. And it happens in exactly the same way. Those hydrogen bonds, not only can they absorb energy, they can actually release energy. And so this is important to us with things like sweating. Um, if you are swimming in a pool, or especially if it's a small body of water or something like that, that can change temperature. It can actually cool off pretty quickly, even if it's hot outside. So the more evaporation that's happening, the more energy that you're losing to the external environment. All right, so here's another property that has directly to do with hydrogen bonds, and that's ice. So if you think of all of these water molecules um, coming in contact with each other, if you've got regular water, like we'll say that this is regular water, okay, those molecules there are sort of spinning around, they're wiggling, they've got certain amounts of energy. And it's almost like the hydrogen bonds are just strong enough to kind of grab on from one to another. Using red on red is probably a bad idea. Sorry about that. So having one grab onto the other, but it's only able to hold on very, very briefly before this guy spins around in another direction or something like that. So with liquid water, they're sort of wiggling, they're moving around. Now, if you want to make those hydrogen bonds much, much stronger, what you have to do is you have to get these things to wiggle around less. And you can do that by taking energy out of the system. And how do you do that? Well, you cool this down. So when you cool water down, it crystallizes, sort of forms these nice, neat little rings. The hydrogen bonds get very close to one another. And if you make it cold enough, you can walk on water. In fact, you can play hockey on water. It's just ice. So there's no great big deal about this. All you do is make water colder and game's on. Now, if you want to make that water liquid again, you add energy back into that system and they start wiggling around a little bit more. They turn into liquid water. They're no longer crystallized. If you want to make it even less stable, you add even more energy into that system. And those water molecules zing around so fast they can't even grab on. There are no hydrogen bonds, and that's steam. So that's it. Everything about hydrogen bonds all has to do with the amount of energy that's in there. So anything that's connected with hydrogen bonds, and there's three big things that are connected together with hydrogen bonds. There's water, there's DNA. One strand of DNA is connected to the other by hydrogen bonds, and proteins. Proteins are actually held together with this. So you can break those hydrogen bonds by adding heat. It denatures DNA and it denatures proteins. We'll talk more about that later. But here's another thing. I don't know what I was talking about. Yeah, we'll talk about that later. Don't worry about it. Okay. One more thing about water, and I sort of mentioned this before. It's a very good solvent. It dissolves like bonds. What I mean by that is if you have something that is already charged, like sodium chloride, like salt, or proteins, carbohydrates, things like that, it dissolves very well in water because water is a charged molecule. Now we have a couple different just terms right here. A solution is just a mixture of substances. The solvent is what's doing the dissolving. In this case, that's water. The solute is the substance that's being dissolved. That would be something like sodium chloride, table salt. Okay, if you're going to put that in, if you're going to put salt in water, it dissolves. Hey, go figure. I know, crazy chemistry. So this is kind of what I was talking about before. Things like sugars and proteins, because they're already charged, they tend to dissolve well in water. Other things that dissolve well in water: nitrites, nitrates, phosphates, um, calcium carbonate. This is neutral, but when you put it in water, it actually breaks apart just like sodium chloride does. Calcium carbonate is chalk. It's what your bones and stuff are made of. So you'll see that all of these things basically are charged molecules, and it shouldn't come as a surprise that the building blocks of life are typically charged particles because they dissolve in water. That's where life originated, and it sort of took advantage of using compounds and molecules that are already charged because they dissolve so well in water. Yeah, we just talked about, actually, I've already sort of mentioned this earlier. I guess I should have been patient and waited. Blah, blah, blah. Just some basic ideas here. Could you describe what happened if you put something like potassium chloride in water? If I tell you that it's an ionic bond, that potassium is positive and chlorine is negative, you should be able to figure that out. Could you identify properties of water that contribute to its unique properties? Let's see. I think that after listening to all this and seeing it, you probably are pretty good with that. If we were to do a practice FRQ, could you describe three properties of water to justify the following statement? Water is essential to all life. So you probably want to talk about hydrogen bonding. You want to talk about water's ability to hold on to heat. You want to talk about its ability to dissolve other like substances. All of the stuff that we've kind of talked about over the last few minutes, be able to do stuff like that. And I'll actually have these PowerPoints up for you. And that's it. Thanks for listening, everybody.